All right, guys. So those of you that are really good at art, you're gonna love this. It's the same thing we were doing yesterday. We're adding an infinite amount of cross sections. Only this time, we're gonna be rotating about an axis. We're rookies, so we're gonna rotate around the x and y axis only. And then tomorrow, when we see each other again, we'll start rotating about another axis besides the x and y axis. We'll keep it simple, either horizontal or vertical. We won't do diagonal rotations because we're not at that level. We'll let your professor at MIT deal with that. All right, so here we go. So here we go. We have this curve. So it says example one, a solid revolution. The region between the graph of y equals 2 plus x cosine x and the x-axis over the interval -2 to 2 is revolved about the x-axis to generate a solid. Find the volume of this solid. So imagine the x-axis like a spindle, and you can rotate it. So imagine you could rotate that. So what's going to happen is this curve is going to go behind the wall, and then eventually it's going to be coming out of the wall, and then boop. See? So hopefully you can see it. So how do you do it? So you can see it visually. So what I would do is first I would reflect across the x-axis. So let me try to plot some points here. So a point right there. That one looks like it's at 1 point there. Let's see, this one's like 1.5. So bam. That one looks like it's at 3. So -3. Bam. And then to the best of your ability, let's see. Almost 3. So there it is. It's not perfect, but that's fine. It looks no, not a fish. Well, I guess yeah, it could be a fish, but check it out. To make it look that three-dimensional, do this. You've seen this before. Well, I guess yeah, it's like a vase, but it's not a hollow vase, right? It's like solid. All that is filled in. Like a solid vase, but it's not hollow on the inside. Now we gotta find a common cross section. So that means either I'm gonna do it. We call it a slice, and the slice is gonna either be a dx or a dy. You ready? You ready? So a common a common slice, a common cross section. So I can cut it horizontally, but if I cut it horizontally, I'm not gonna have a common cross section. If I cut it vertically, my common cross section is gonna be what shape? Do you guys see it? Let's see. I'm gonna cut it. Look, here's my slice. Shh, I'm cutting it. Pretend this is like I don't know, a cake that looks like this. And then yeah, it's a circle. In the math community, they call it a disc. Why do they call it a disc instead of circle? I don't know, guys. But you can call it circle. Not a big deal. See, it doesn't matter where you cut it. That's cut right on the y-axis. I'm gonna cut it right here. It doesn't matter where you slice it. All these cross sections are discs or circles. Do you guys see that? And that's what you're adding, guys. You're adding an infinite amount of circles. Those are my cross sections. So here's how you do it. Area of a circle is equal to pi r squared. Notice that I put a of x. So I don't want it in terms of r. I want it in terms of x. So a of x equals pi parenthesis the radius. What's my radius? It's this in green right here. From the x-axis all the way to the top of that curve. I wonder, is there a formula that dictates that radius value or that y value? What is it, guys? Yeah, 2 plus x cosine x. That will determine that r at all times. So 2 plus x cosine x, close it, and put a square on it. There is my area cross section. That is what I'm adding up an infinite amount of times. So if I want to add them up, what do I got to do? Start the letter I. Integral. So volume equals pi on the outside, integral from -2 to 2, -2 to 2, of 2 plus x cosine x, close it, squared dx. All right, I'm going to go slow on this part because we tend to have a lot of mistakes on here. If you try to type this in like this, which some of you are very good with paying attention to detail, and you won't mess up. But some of you are not. You just go with the wind, and you're just like, oh, I'm going to type that in. And you go pi. Look, I'll show you what I'm talking about. Math 9, negative 2 to 2. And then you come in here and then open parenthesis, 2 plus, and I already forgot it, 2 plus x cosine x. 2 plus x cosine, it opens up parenthesis, x, close. And then look, did I already mess up? Yes. What am I squaring? I'm squaring cosine x. But I don't want to square cosine x. I want the square 2 plus x cosine x. But some of you will not catch that. And you'll just do it like this. And then, boop, that's the wrong answer. Here it is. Here's the right answer. So let me close it. Close. So delete. Delete. Boom. That's the right answer. If you are prone to making mistakes, here's a hack that you can do to never make mistakes. So, Chav, what's a hack? You need that equation anyways. Sometimes you need it like 2 or 3 times. Type 2 plus x cosine x into y1. 2 plus x cosine x. And there it is. That's your r. That's your radius. So I can just come back and I can go pi, math 9, negative 2 to 2. And then I can just go, it's pi r squared. So alpha, trace y1, square this dude, put an x on it. Done. See? How do we feel? Okay. Do not use calculator language when you're doing your homework, assessments, assignments. You don't type y1 in your handout or whatever you're writing. Type this in your handout. So there it is, 52.4288. How many digits after the decimal? At least. You can always write more. 52 point, was it 488? 488. And there it is, guys. What did you guys think of the first one? Not bad, right? So it's the same as what we were doing yesterday. We're just adding up an infinite amount of cross sections. All right. Do you guys remember from pre-cal? You're going to like this one, I hope. Do you guys remember how cosine x looks? Do you guys remember how sine x looks? Okay, so I'm going to draw a little sketch here because I don't want to take up this space here. Here's how cosine x looks, and here's how sine x looks. So we're looking at, look what it says. The region in the first quadrant enclosed by the y-axis, the graph of y equals cosine x, y equals sine x, is revolved about the x-axis to form a solid. Find the volume, no calculator. So they want us to find this. This is the region that I'm looking at, and I'm going to rotate that about the x-axis. So it kind of looks like a shark fin, but on the y-axis, sticking out. And then we're going to rotate it. So it's going to look like this. So so now I'm going to go ahead and draw my sketch. It's kind of fun, guys, to do all these little sketches here. So I'm exaggerating them. So let's see. It's going to look like that. Where does cosine x and sine x hit? When x is pi over 4. And that coordinate, if you wanted to know, is pi over 4 comma square root of 2 over 2. See? And I think we're good. Let's rotate it. When I rotate it, let's see. Point doesn't have to be perfect, guys. Yeah, I like it. It's not super awesome, but I like it. When I do my slice, with respect to, so here's my slice. I'm cutting it. Have you guys, especially in robotics, you guys have seen this. What is that? What is that slice? What is that slice? Starts with a W. It's a washer. It's a washer, guys. Where it's this that's consumed. It's a washer. I'll buy some washers tonight at Walmart and I'll send them to you. I'll put holy water in them. You can put it on a string, make it a necklace for the AP exam or something, or hold on to it. It works, guys. We got 100% with those washers. 100% qualifying. No, but that's a true story. All right. How do I find the area of this washer? So let's do some geometry. Let's do some side notes. So this is called big R from the center all the way to that one. That's big R. And this is called little r. If I want the area of the washer, you go pi r squared, the big circle, and I subtract the little circle. Yeah. So here it is. Here is my area. Pi big R squared minus pi little r squared. Is there something I can factor out? Yeah, the pi's. Because the r's are different values, right? Capital R and little r. Pi's. So big R squared minus little r squared. So there it is. That's my formula. I'm just going to call it area. Equals area for the washer. That's my formula. Pi big R squared minus little r squared. See? It doesn't matter where you slice it. I guess if you slice it at pi over 4, you have no washer. But, you know, we're adding up all the infinite washers from right at 0. And at 0, technically you have a disk, but that's fine. That's part of the formula. Anyways. And then all the way from 0 to pi over 4, you're going to have washers. And you're adding them all up. Does that make sense? All right, so there it is. And remember, that's what the green stuff is, the shaded region. That's what was rotated. What happened there? All right, so here we go, guys. I'm going to go volume equals pi on the outside, integral, let's see, 0 to pi over 4, giant parenthesis, the big R. The big R is the distance from the x-axis to the top of that curve. I always like to reference the original curves. So how do I figure out that purple distance? What curve is that on the top? Yeah, this one's cosine x, guys, because cosine x starts at the y-axis. So this is going to be cosine x with a square on the side minus, Trav, what are you doing? That's big R squared, guys. Now I need little r squared. Little r is this one in green. This one in green right here. That's little r. What curve is that guy? That's sine x. So that's little r. Sine x, close it, squared. Dx. Have I confused anyone, guys? Okay. So look, this is going to give me my volume because you're adding up all the cross sections. Remember, that integral means you're adding up an infinite amount of cross sections, which is going to give you that volume. You can always let the units help you out. This times dx, the change in x is going to get a three-dimensional surface area times your, yeah. Okay, anyways. Are we okay, guys? Have I confused anyone? All right. My radius is squared, and that is radius. That's my equation that represents a radius for any washer at the x value. No, cosine is my big R. Well, yeah, the big radius. See, do you see this guy? The distance from the x-axis to the top of that curve. That's the big R. So, look, and this is my area. That's what we did yesterday, right? This is my area cross section. So my big R is the cosine x, and the little r is the sine x. Yeah, because it's just a constant pi. You can leave it on the inside if you want. All right, guys. So here's the issue on this. Notice that it says no calculator. Most of the time, you will have a calculator with these. But if there's properties or something that you can do to, well, I think in the AB exam you're fine, but the BC, I think you're still fine. But if there's ways to make stuff simpler, you should try. So side note, let's do a quick pre-cal lesson. Remember when you guys were in pre-cal, we said cosine A plus B was cosine A cosine B minus sine A sine B. Do you guys remember that? We did talk about that, right? Last year? Yeah, no, I thought we did a whole semester on that, or a whole 3 weeks. So if I change that B to an A, cosine A plus A, then that would be cosine A minus sine A sine A. And so now this is cosine squared A minus sine squared A, which is exactly what I have here, but instead of an A, it's an X. And A plus A is 2A. So from that, we can infer and replace. So volume equals pi integral 0 to pi over 4 of cosine 2x dx. Yeah, let me know. Let me know if I lost you. Have I lost anyone? Tell me, Salali. Dime. If this one comes out on the exam, I will give it to you. I'll give you if it comes out on our exam. I don't see it. Don't quote me, but I don't see it coming out on the AP, quote unquote, because it's not a pre-cal exam. It's a calculus exam. All right, you guys ready? Antiderivative. So pi, leave it alone. Bracket. Antiderivative of cosine is sine. So sine 2x. This is a linear. If I were to do chain rule, I would have multiplied by 2, but I'm doing integration. So you do the reciprocal of 2. Put a half on the outside like that. 0 to pi over 4. That half, okay, I'll slow down. Some of you are still doing, bless you. Some of you are still leaving the half when you're doing evaluate upper minus lower, which is fine, guys, but you're making life harder for yourself. Make life easier. Both terms are going to have that half. Just factor out the half. Bless you. Bless you squared. So make life easier for yourself. If you want to leave the half, go ahead. But make life easier for yourself. Both terms are going to have it, so just factor it out. So pi over 2, big bracket. I'm going to do the sine 2x with the pi over 4 in there. So sine of, if I plug the pi over 4, I get pi over 2. Minus sine, if I plug in the 0, I get 0. A little bit of pre-count, not extreme, baby pre-count. Sine of pi over 2 is 1. Sine of 0 is 0. So you just get pi over 2. If you had a calculator, you can just type in this equation on the top. So look, check it out, guys. What am I going to do? Yeah, let's just type it in. Math 9. Let me put the pi on the outside. Second insert, second pi. What was it? 0 to pi over 4? Pi over 4. And then look, open parenthesis, cosine x, close, squared, minus, open parenthesis, sine x, close, squared, close again, and put an x there, and voila. Yep, that's pi over 2, guys. Check it out. Second pi over 2. Yay! Bless you. Cool or not cool? Okay. How do we feel, guys? Salali, we're doing all right? Okay. All right, let's go to the next one. Ooh, I like this one. I hope you guys are going to like this one, too. You ready? It's a true-false question. If the region enclosed by the y-axis, the line y equals 2, and the curve y equals square root of x is revolved about the y-axis, the volume of the solid is given by the definite integral 0 to 2 with a pi on the inside. You can put the pi on the outside if you want. Y squared dy. Justify your answer. All right, let's see, guys. So here's my grid. And they told me the equation is y equals square root of x. It's not to scale. I'm going to put not to scale. Y equals square root of x. And y equals 2. That's y equals 2. And so they intersect right there. And it's enclosed by the y-axis. So they're talking about this region right here. And I'm rotating this about the y-axis. So if I rotate it about the y-axis, it's going to look like this. It almost looks, so look at this. Oh, this is going to be so awesome. My slices, the slices are not, I know, guys, I know it's so hard because we're already like at the end of the day and everyone's tired by now. So it's easier to do math in the morning than it is in the evening. All right, your slices. Instead of being perpendicular to the x-axis, these are not dx's because I can't have a common cross-section that way. I need to make sure that the section is the same all the time. So check it out. They're dy's. Do you guys see that? They're dy's, guys. My slice are dy's. Look, it's right here. I'm going to cut it like that. Bam, cut it. See? Because it's rotated about the y-axis there. So those are all dy's. Those are all dy's. So that means you need this expression in terms of y. So this equation, y equals square root of x. So this equation, so let's see, y equals square root of x. I'm going to square this. Square this. Child, why are you doing that? Because I need x equals y squared. This is what I need. Because my radius is in terms, look, check it out. What's the distance? Okay, volume. I'm going to just write it. Volume equals pi integral. My lower limit is 0. My upper limit is what? 2. And then my radius is the distance from the y-axis to that red curve. And that red curve is defined by y squared. So y squared and then square it again. Do we know what we're squaring it? Yeah, because area of a squared, let me write it. Area of a squared is pi r squared, guys. And r is y squared. See? So hopefully you can see this. So then hopefully I'm going to put a happy face there. Hopefully you can see that. So y squared squared. So what's y squared squared? Y to the 4th. Laws of exponents. You can see they don't go away. So true or false? False. What do you think, Kanduru? Did we go hard in there? Was this hard in the paint? Oh, okay. Kobe Bryant would approve. How do we feel, guys? Caitlin Clark would approve. I don't know about Reese, though. Yeah. She's a baller. I'll stop. All right. Example 4. Let R be the region in the first quadrant bounded by the graph 8 minus x to the 3/2, the x-axis, and the y-axis. Which of the following gives the best approximation of the volume of this solid? Okay. Obviously, you need a calculator because there's no decimals there. But if I didn't, I want you guys to get to a level where you feel comfortable of how this looks without the assistance of a calculator. So when x is 0, I'm at 8. And then where do I cross the x-axis? So let's see, 8 minus x to the 3/2 is without a calculator equals 0. So move that to the other side. 8 equals x to the 3/2. And then to find my x value, you got to raise this to the 2/3. So raise that to the 2/3. So x equals the cube root of 8 is 2. And 2 squared is 4. So that means this looks more or less, don't quote me, but it looks more or less something like this. I have a point at 8, not to scale. And then I have a point at 4, 0. I have a point at 0, 8. And I have a point at 4, 0. And I have to be going down. This negative there. So it probably has something like that. See? And I'm rotating this about the y-axis. Oh, man. The x-axis. I almost made a mistake. The x-axis. So let me stretch this guy. And so here it is. Let me change the color so they're not all. So there, that's the maximum there. And it looks something like. That's 0, negative 8. And then how does it look? Oh, let me change the color again. Looks like that. So when I do a slice perpendicular to the x-axis, what type of slice is this? A circle, a disc. Cool or not cool? All right, so here it is, guys. Volume. Volume equals, you're adding the infinite amount of cross sections. Volume equals pi integral from 0 all the way to 4. So these are dx's, right? No, you're good. Those are dx's. They're perpendicular to the x-axis. That's a change in x. Those are dx's. 0 to 4. And your radius is the distance from the x-axis to the top of that curve. So this one in purple. From here to that curve. So that curve is this one. So it's going to be 8 minus x to the 3/2. Close it, put a square on it, dx. Do not leave it alone. I mean, I guess you could expand it by hand, but there's decimals there. Just type it in the calculator. So here we go. Take my calculator. Pi. Oh, man. Second pi. Pi, math 9. From 0 to 4. And then I'm going to open up a parenthesis, and I'm going to type in there 8 minus x to the 3/2. 8 minus x to the power 3/2. And then close, and then there it is. So I'm going to square that. And I think we're good. Boom, boom, close. Yep, that's it. And then put an X on it. Be careful. Bam. Did I mess up? Is that answer in there? 361.9? 361.911. I think that's what it was. Yeah, I can tell this is not an AP question because it doesn't have 3 digits after the decimal. That's fine. We're almost done, guys. Last 2. Let R be the region enclosed by the graph y equals x squared, line x equals 4, and the x-axis. So that means we're looking at quadrant 1. Q1. Quadrant 1. Child, why aren't we looking at quadrant 2? Because it's enclosed by x squared and x equals 4 in the x-axis. I don't have anything, you know what I mean? Like if I were to go x equals 4 and then the x-axis, it stops here at the origin. So that means the only way they're enclosed, remember enclosed, is if I'm looking at that. Does that make sense? So underline the word enclosed. So there it is. So I'm gonna erase it and I'm gonna draw it better. So here's me drawing it better. And then I'm gonna go red x squared all the way to 4, not to scale. And I'm gonna say that's x equals 4. What's 4 squared? 16? Okay. Did everyone know where I got the 16 from? Yeah, when x is 4, plugging a 4 in here, 4 squared is 16. So it's not to scale. Obviously, my scales are totally off. 4, 16. And I'm rotating this about what? The y-axis. So rotate it about the y-axis. So it's going to look like this. Symmetrical on the y-axis. There we go. If you wanted to see that. And check it out. So what type of cross section do I draw it? Is it a dx? Is it a dy? It's a dy. Check it out. It's this one right there. See? The cross section's a dy, guys. What shape is it? It's a washer. Do you guys see how it's a washer? What's up, Salami? Tell me. Oh, yeah, no, it's a weird type of bowl. You're right. This will hold water, quote unquote, because it is a solid, right? But this on the side, it's a weird type of bowl. This is filled in. This is a solid. Like the sides are perfectly square like that, and then this holds stuff. Can you guys see that? Okay. Yay! Look at that. All right. By the way, if you downloaded WinPlot, you can do all these cool stuff with revolutions and stuff. All right, there it is. There's my washer. Notice it's a dy, so I need this guy in terms of x equals something with y. So I'm gonna write y equals x squared, and I'm gonna go square root. X equals the square root of y. So this would be a perfect example of something that would be done by hand without the assistance of a calculator. Bless you. All right, so here we go, guys. So volume equals pi, and it's a washer. If it's a washer, we're going to do big R squared minus little r squared. We're doing this. We're doing this guy right here, that equation. Pi, big R squared minus little r squared, guys. So I come back, and here we go. Integral. With respect to y, what's my lowest limit? 0. What's the biggest? Perfect. Excuse me. Parenthesis, big R. The big R is always what? It's a constant. 4. 4 squared. It's always, no matter where the washer is, it's always 4. The distance from the y-axis to that vertical line. Do you guys see that? Minus, parenthesis, the little r is the distance from the y-axis to this curve there, which is y equals x squared. But you're not going to type x squared. You're going to type what? Square root of y, close it, squared, close it, dy. Are we cool? Tell me, Salali. All right, check it out, guys. This is an example of one you would do by hand. So volume equals pi integral 0 to 16. 4 squared is just 16. Square root of y squared is just y, so 16 minus y, dy. Equals pi on the outside, antiderivative, so I'm going to put a bracket. Antiderivative of 16 is 16y. Antiderivative of y is y squared over 2. Close it from 0 to 16. You just have to worry about the 16 because everything's going to zero out with the 0. So I believe 16 times 16 is 256. So I'm going to write over here, I'm going to go equals pi, parentheses, 16 times 16 is 256, minus 16 squared is again 256, but if I divide it by 2, it's 128. And 256 minus 128, 128. So 128 pi. We'll verify it. Even though this is probably no calculator question, we'll verify it with a calculator. So how would I do it with a calculator? I would not put the pi in there. I would just go math 9, what was it, 0 to 16? 0 to 16. And then I would go 4 squared minus, if you want to put the parenthesis with a square root of y in there, you can. You can do this, square root alpha y. I just don't like it because it makes me slower. Squared alpha y. So there it is. Put a pi next to it. It makes me slower, guys. Does it matter what letter is in here when I'm putting it in the calculator? No. Like, right? When I'm putting it in the calculator, it doesn't matter. On paper, it does. Okay. So I don't want to confuse you guys. When you're doing the work, when you're doing this, definitely have a y in here. Cool or not cool? When you're putting it in the calculator, does it matter? No, just do a hack. It doesn't matter what letter you put in there. I'm just going to push enter. Just push X. Push T if you want. But X is the fastest route. X, and then put X on this guy. X. See? It doesn't care what letter it is. It's still going to be 128. That is why we called it a dummy variable when we're doing definite integrals, and it doesn't matter what letter we have. Cool or not cool? Okay. Last one, and then we'll call it a day. I know that you guys are tired. All right. Let R be the region enclosed by the graph y equals e to the x, y equals e to the negative x, y equals e to the x, and x equals 1. Which of the following gives the volume of the solid generated when R revolves about the x-axis? Okay, guys, here we go. Before we even start, so I'm drawing really little graphs because I want to fit everything in here. Here's how y equals e to the negative x looks like. This is y equals e to the negative x. Here's how y equals e to the x looks like. Y equals e to the x. Hopefully this is not new to you. I hope that we have that already on lock. So when I graph all three of them, I'll graph it a little here and then I'll blow it up in a little bit. So when you put all three in the same, and x equals 1. This is the region they're talking about. Do you guys see that? That's the region they're talking about. And I'm rotating that about the x-axis. So here it is. I'm going to do a grid, a large grid here. And here's how it looks. It's going to look something like, let's see, bam. And then this guy goes down like that. And then, and there it is. And then I'm going to rotate this about the x-axis. So there's a little gap here. So, boom. And I'm trying to keep it symmetrical, more or less. And then this guy. Did I do it wrong? No. Hold on, hold on. I'm dumb sometimes. There we go. Now we got it. No. Boom. Boom. Say boom. And point. Okay, this point should be more this way. There we go. And why can't I see it? Boom. There we go. And it's not super awesome, but it's kind of okay. Does it look okay, guys? There's a hole right there. There's a hole right there. But every cross section in between that. Sorry about that, guys. I should have drawn it better. I should have just used the copy paste feature of this thing, but that's fine. What shape is that? It's a washer. Do you guys see it? Yeah, I should have put this point more down. I should have put that point more down so it would have been more symmetrical, but that's fine. That's fine. Not my best work, but that's fine. I should have put this point here more down and it would have looked more symmetrical about the x-axis. But that's okay. It looks good enough. Does it look okay for you guys or no? All right, here we go. That's a dx. So volume, let's go right into it because that's what we want anyway, is the equation. And this is the last one. Volume equals pi integral from what to what? 0 to 1. And then let's see, big R squared minus little r squared. That's what we're doing. So the first thing I would do is delete A, B, and C because there's no pi on the outside. So it's between D and E. Big R squared, I guess just knowing big R squared minus little r squared, I guess you can just get the answer there that way. From the x-axis to the top of that top curve is y equals e to the x. So e to the x, close it, squared, minus, open parenthesis, the little r squared is from the x-axis to that little curve down here. That little curve down there is y equals e to the negative x. So e to the negative x, close it, squared, close, dx. So law of exponents, an exponent raised to an exponent, you're going to multiply them. So here's what you have. Volume equals pi integral 0 to 1 e to the 2x minus e to the negative 2x dx. Which one is that? How do we feel? Okay. You guys want to take a little break? All right, so I'm going to pause this because I want to do one more. Yeah, it is. All right, go to the activity. Look at number 4. Don't worry. I'm giving you a free one, guys. It says, for problem 3 to 6, find the volume of the solid generated by revolving the region bounded by the lines and curves about the x-axis. So this equation right here, y equals square root of 9 minus x, that looks like this, guys. That looks like here's negative 3, here's 3, and it looks like that. It's a semicircle. Because the equation of a circle is x squared plus y squared equals r squared. And if it were to be a plus minus, you would have a whole circle. But you don't. It just says square root. And then when I rotate this about the x-axis, it looks like this. And then I have this. When you do a slice, that's my slice. So think about it, guys. When you have this shape and the semicircle and you rotate about the x-axis, what type of shape are you going to have? A sphere. And so why I love this one is if you did the geometry formulas for volume of a sphere, that's the same. You get the same answer. Let's do it with calculus, and then we'll do it with geometry, and let's see if we get the same thing. Of course, we're going to get the same thing, but this is why I thought this one was cool. Volume equals pi integral negative 3 to 3. You can actually do it from 0 to 3 and double it, but that's fine. We'll do negative 3 to 3. What's my r? The r is the distance from the x-axis to that curve, and that curve is this. So parentheses, square root of 9 minus x squared, close it, squared dx. Whenever you square a square root, they go away. Does that make sense? So now I have, so this is one where you can do it by hand. Pi integral negative 3 to 3 of 9 minus x squared dx. Because I squared the square root. And now here it is. So pi bracket, antiderivative of 9 is 9x. Antiderivative of x squared is x cubed over 3 from negative 3 to 3. This time there's nothing to factor out because, well, I guess you technically could, but don't factor anything out. Leave it alone. Upper minus lower. If you have one term, you could do that, right? But upper minus lower. So 9 times 3, that's 27. Minus 3 cubed. 3 times 3 is 9. 9 times 3 is 27. Divided by 3 is back to 9. So 27 minus 9. That's the upper. Minus, parenthesis, 9 times negative 3 is negative 27. Minus, what happened? Minus something, also plus. And again, I'm going to get a 9. So it looks like I got pi, and then this looks like 18 minus a negative 18, so plus 18. So 18 plus 18, that's 36 pi. Are we okay, guys? Now check it out. This is what's so awesome. I'm already kind of warmed up a little bit because I did this one earlier. But I just want to say, like, look, I don't want to be fake, and I want to make sure that this is also the same thing if we do geometry. So using geometry, let me change the color. Let's change it to, what's your favorite color? Purple? Using geometry. What's the radius of this sphere? What's the radius of the sphere, guys? 3. Volume of a sphere is 4/3 pi r cubed. That's the volume of a sphere. So look, using geometry, 4/3 pi, parentheses, 3 to the third power. So we get 4/3 times 3 to the third power is 27. 3 goes into 27. I still have a pi, so let me put the pi there. 3 goes into 27 9 times, right? 9 times 4, 36. OMG. Are you shocked that we got the same answer, 36 pi? Isn't that cool that we can verify stuff with calculus and geometry? And I think that is so cool, guys. But you got to realize that it's a sphere first, right? Like, well, if you're just going through the motions, maybe you don't realize it. But if you were to be in an exam, I would think that would be valid if you recognize, oh, this is a sphere, and then you don't even bother with the calculus route. Like, volume of a sphere is 4/3 pi r cubed. Volume is 36 pi. I would count that correct if I'm reading and I see that question and you correctly answer it, because you recognize. I would probably go to the table leader, but I would think that they would give it to you. Cool or not cool, guys? Do you guys want me to do one more? You guys want me to do number 1 as a visual? All right. So we'll just do this one together. You have a visual, guys. It always helps to do a visual. Find the volume of the solid generated by revolving the shaded region about the x-axis. So here it goes. I'm spinning that. And it looks like -1. So here's my slice. Convenient for me. It's always going to be a disc or a circle. Do you guys see that? So this is a dx. I need my equation in terms of x. You can leave it like that. No, don't leave it like that. You can either y equals, let's see, 1, 1, 2, negative half x plus 1. What? Yeah, that's a dx. So I need it in terms of x. There it is in terms of x. The equation. The expression. You could have also just moved this, guys. 2y equals negative x plus 2, divide by 2, divide by 2, divide by 2. Y equals negative 1/2 x plus 1. It's the same thing. I just saw that the slope was a negative half. Yeah, I went 1 down and 2 to the right, and y-intercept of 1. But whatever. It doesn't matter. However you want to do it. Algebra is algebra. This is the r. The r is the distance from the x-axis to that curve. And so let's see. What am I going to have? Pi integral 0 to 2, giant parenthesis, negative 1/2 x plus 1, close it, put a square on it, dx. Use your calculator. You're going to use calculator for most of these. If there's a question that it looks like you can use it, you can do it without a calculator, then don't. You can expand it also and do it without a calculator, but this one just use your calculator. Use a calculator, give me the answer, and we're good. That makes sense, guys? Can you guys take it from there? All right, we're done, guys. You guys did a good job. Did all this make sense?